There we go. Okay, we're going to get started. Okay, well, thank you everyone for joining us for October's DataWorks Maryland meetup. I'm extremely excited to have Ryan Carr from Unveil talking about enabling cross-boundary data science with privacy-enhancing technology. I've been trying to get an Unveil speaker for a while, so I'm extremely honored and excited to have Ryan here. Before we get started, I'd like to go through some just brief announcements, thank our sponsors and just some upcoming events, and then I'll hand it over to Ryan. So to get started, Varen Technologies, excuse me, is a company that's been supporting the meetup for several years now. They do a lot of interesting work for the government and do everything from software engineering to DevOps to data science. So if you're interested in learning more, please feel free to reach out directly or reach out to me. Clearage Technology is another company that's doing defense contracting work in the Maryland area. They've actually done some recent events on their own. They did a tech talk a couple weeks ago that looked really interesting. I think the videos are going to be available at some point, so it's something might be worth checking out. Aries Ventures is our company or my company, and we focus on data science, analytics, software engineering for government, customers. If you're interested in learning more, I love, sharing what we're doing. So please reach out. And then Microsoft, everyone kind of knows Microsoft. They started sponsoring the meetup recently, and they've been doing some interesting events. And they're, moving into the Annapolis Junction area, and they're doing a lot of stuff with government contracting also and data science. So if you're interested in learning more about what they can offer, please reach out. So next month, we'll have a speaker from MITRE to discuss the Defend, which is focused on cybersecurity and is related to like the MITRE attack work that they're doing. So if you're interested in like data ontologies and data science and just like knowledge management, that would be a good event to attend. We're still trying to get the conference. Can always use recommendations, help, any suggestions. If you're a speaker or you're interested in just participating, please reach out. And with that, so Ryan Carr serves as the CTO and VP of Engineering at Unveil, pioneering privacy enhancing technology, protecting data and use. And that's actually the thing that was of interest to me. Like if you guys have ever worked with data, encrypted data, generally you have to decrypt the data to work with it, and that's where Unveil really provides an interesting solution to allow you to work with that data while it's actually encrypted. He has experience working at Johns Hopkins APL. And he has expertise in large-scale analytic systems, distributed algorithms, AI, game theory, social learning, and applying cloud computing techniques to simulate and analyze complex interactions among large numbers of autonomous agents. I'll let Ryan do more introduction or give you a little more background. But for questions, the way that we were going to handle it, if you have a question, feel free to put it in the chat. Either on YouTube or Zoom. I'll be monitoring that, and I'll ask Ryan the questions at the appropriate time. So with that, Ryan, I'm going to stop sharing. You can share. I'll mute myself, and you can take over.
Okay, great. Thanks, Jason. So yeah, as he said, I'm Ryan. I am the CTO at Unveil. Unveil is a 30-person startup. We're based in Fulton, Maryland. And yeah, we do work with homomorphic encryption and privacy enhancing technologies, and I'm excited to talk to you today about some of the technologies that we do and some potential use cases for them. So this is going to get somewhat technical at points. I've attended a couple of these talks, attempting to thread a bit of a needle where I get deep enough into the weeds to interest the hardcore software engineers among us. But sort of stay at high enough level to keep people's eyes from glazing over, right? If you're not a big math person. So there are going to be some numbers and stuff on these slides. I am going to talk through step by step how a sort of algorithm processing homomorphically encrypted data is going to work. So I guess let me know how I did. Hopefully I thread that needle. So the title of the talk is Enabling Cross-Boundary Data Science with Privacy Enhancing Technologies. So rough outline is, first I'll talk about what do I mean by cross-boundary data science, and then I'll talk about what are privacy enhancing technologies. That is kind of an umbrella term that has kind of gained popularity in the industry, which is why we kind of used it in the title. Homomorphic encryption is one of those technologies, and it's the primary one that we use at Unveil. So I'm going to talk through a primer as to what exactly is HE and show a couple of example use cases for it. First one is going to be private information retrieval, and I'll sort of go through in detail how that algorithm works. And then I'll talk about encrypted machine learning and have a few slides on that. I won't go into quite as much detail, and there's a good reason for that, and you'll see it in a minute. And we'll sort of talk about some applications there. Okay, so let's kick things off. Cross-boundary data science. What do I mean by that, right? A lot of data sets, particularly ones that we deal with in the Central Maryland and Northern Virginia area, have boundaries to them, right? Limiting either where they can move or how people can interact with them. And in a lot of cases, the data is not necessarily data that like sits on a disk. It's contents of an interaction between somebody and a data set, like a search terms, things like that. Or it could be metadata or things like that. And so the different types of boundaries that the stuff that I build helps people deal with are things like security classifications, top secret SCI type classifications, which I bet a lot of people on this call are familiar with. There are also privacy regulations. So, things like HIPAA, things like GDPR. A lot of cases, the boundary is literally like a physical border between countries. So in the banking sector, for example, there are a lot of countries with banking regulations saying, no data about our citizens can leave our borders. They call those secrecy jurisdictions. And then a lot of times it's not necessarily a hard boundary to how the data can move, but it's a competitive interest that's sort of preventing two people from talking, right? So an example of that would be if you are in the financial sector, you're doing merger and acquisition work, and you want to do some research about a company that you're interested in buying, right? If you are a big player there, if you're like Goldman Sachs or something, the fact that you're looking into that company might suddenly make the company's value shoot up, might cost you an extra $10 million if you could buy the company, right? So you might hold off on doing some interactions with other firms that sell data like that, like Thomson Reuters, for example, with the intent of keeping it under wraps that you're interested in that company. And we have products that can kind of help with that. So privacy enhancing technologies is something that can basically allow searches, analytics, and certain types of machine learning across these kinds of boundaries. So what is privacy enhancing technologies? That's kind of an industry term. It describes a lot of sort of technologies that are just now moving from academia into something where it's actually applicable in business use cases. And it covers a lot of different kind of specific technologies. And so that's why we've got that kind of web right there on the left. And it also covers like certain techniques that you might use different technologies to do. So at Unveil, for example, we use homomorphic encryption, and some of our solutions do private set interception. But some other things that you might have heard about in the privacy enhancing technologies umbrella are things like differential privacy. I know that's something that's of a lot of interest to data scientists. Secure multi-party computation and trusted execution environments. So this would be something like Intel's SGX technology that basically tries to wall off an area of your processor, right? So these are all things that are under the privacy enhancing technologies umbrella. That word enhancing, I don't really particularly like that word. It's kind of what the industry has settled on, right? But at Unveil, enhancing means sort of to me that you're taking something that already exists and making it better. And Unveil, the stuff that we sell and the use cases I'm going to talk about today, they add something to nothing, right? They allow privacy to exist in the kinds of interactions where privacy was completely impossible before. So for us, it's more like a privacy enabling technology, I guess. But that's just kind of like a pet peeve of mine. So yeah, over here, to try and help people make sense of how do all these things compare with each other, we've got this axis of most secure to least secure. Certainly somebody who is, an academic and familiar with all of these things might quibble about certain positions of things, but my justification for this is we have homomorphic encryption as the most secure. I'm going to get into detail about that in a minute, but homomorphic encryption basically provides the same kind of computational security guarantees that you have with encryption that you're already using, like AES or RSA. Below that, I have SMPC protocols that involve multiple parties. There are a lot of solutions out there right now that are trying to leverage multi-party, meaning 3 or more parties, SMPC protocols, where the security guarantee comes from an assumption that not everybody else in the system. So if you're one of those parties, the assumption is not both of the other parties or all the other parties in the system are working against you. And in my world, we deal primarily with the federal government. And of course, the federal government, if they are one party in that kind of protocol, they are never, ever going to trust that everybody isn't working against them. So that's why we have that down there in the second most secure thing. And then trusted execution environments. This is something that is sort of a cool idea and can kind of work sometimes in practice. But the problem is that like new vulnerabilities are released about them constantly. So if you follow the news around Intel SGX and things like that, there was just another attack called SmashX published a couple days ago. So the general problem in practice with them is that the processors, the way that trusted execution environments work is they try and wall off a section of the processor so that other processes running on there can't access the memory. The memory is encrypted every time it's outside of that little SGX enclave, so to speak. And processors are just so complicated that even Intel doesn't fully understand how they work. And so people keep finding attacks that poke through those security guarantees. So anyway, I'm spending so much time on this because people may not have really heard of it much now. A lot of these technologies are just now moving over into something that's actually relevant. But I do feel personally, and now Gartner has a big quote that kind of backs me up, that this is something that's really gaining momentum. And they expect that in 4 years or so, 50% of large organizations will have some kind of privacy enhancing technology in their system. Okay, so like I said, at Unveil, I primarily work with homomorphic encryption. So I want to take a couple slides and just explain, what is homomorphic encryption and try and give you a general sense, just enough that you are going to be able to understand the sort of use cases that I'll take you through later on in the slide. Homomorphic encryption, admittedly, is extremely complex, and so I'm going to point you to some open source resources that you can dig into on your own if you want to get more detail than what I'm about to offer here. And I'm also going to take a minute to just talk about how does encryption work in general, right? I know we probably have a lot of people on this call who already know everything I'm about to say, but just in case that we don't, properties of modern encryption, meaning everything since 1970 or so. Things that you're already using right now to watch this presentation being streamed over YouTube, right? AES, RSA, things like that. The way that they all work is they have a plain text message format, right? Some way that you specify what your message's contents are going to be. And they have an algorithm that encodes that plain text into a ciphertext, such that somebody can't look at that ciphertext and tell what its contents are. And that encoding algorithm is built around a mathematical construct called a trapdoor function. A trapdoor function is something where if you have a specific secret key, which is usually some big number or some combination of numbers or something like that, it becomes very easy to take that ciphertext and decode it back into the plain text message and get out the data that you could store it in the encryption. But if you don't have that secret key, then the algorithm provides computational security guarantees that basically say the smartest mathematicians in the world have studied this problem for decades, and the best solution anybody has come up with still requires you to try some crazy high number of possibilities that nobody is going to be able to actually do practically. So something like 2 to the 80 would be sort of the minimum threshold. A lot of things like AES, for example, will have you do like a 2 to 128-bit exhaust. Basically, something more than the number of atoms in the universe, something so big that nobody's ever going to throw enough compute power against it to break the mathematical problem that's protecting the data of your encryption. So everything that I've just said applies to all the encryption that you may have already used or that you definitely have used without knowing it. Homomorphic encryption does all of that stuff. But the one thing that makes it different is that it permits operations on ciphertext without having access to the secret key. So all of the encryption that you use today, that transformation from the plain text message to the ciphertext message makes it so that you can't really do anything with that ciphertext message other than decrypt it back to the original message. So it's useful for storing data on disk, for example, and then coming back later and decrypting it and getting it back out. There are sort of complicated algorithms for two parties to agree on a secret key and exchange a secret key without other people seeing it. And that's what's used in TLS. That's what's used to encrypt the network connection you're using to view this video right now. But again, that's just one side encrypts the message and sends it over, and the other side decrypts it, right? You can't actually do anything with those ciphertexts. With homomorphic encryption, you can take those ciphertexts and still perform some meaningful operations. And there are a number of homomorphic encryption algorithms out there right now that basically work with different data types is the main difference between all the latest generations of them. So BFV and BGV work on integers. CKKS works on fixed point real numbers, and TFHE is used for Boolean logic. I'm going to now tell you some details about BFV. So that's the thing that we're going to use for most of the rest of this talk. BFV stands for Brzezinski van Verkaderen, which is just the authors of the crypto system, right? So it's just the names of three scientists. The way that BFV works is, just like regular encryption, we've got our plain text message, and we can encrypt it and decrypt it into a ciphertext. In homomorphic encryption, the security is based on the hardness of ring learning with errors. So ring learning with errors is the name of that trapdoor function. And so in order to get the security to work, the plain texts have to be polynomials. And the coefficients on those polynomials, and when I say polynomial, I guess one thing that's a little bit weird about homomorphic encryption that you might not be used to is most people who are not like theoretical mathematicians, the only encounters that they've had with polynomials are a function where you put something in as input and you get something as an output, right? So in BFV and homomorphic encryption, a polynomial is kind of like a word that means something. It's just a thing that can be encoded and decoded. You don't necessarily, we're not ever going to fill in anything for X in this polynomial, right? This particular polynomial just corresponds to one of the valid messages for the encryption. And so here we've just happened to choose 4x cubed plus 3x squared plus 2x plus 1. That's my plain text message that I've decided that I'm going to use using however I'm deciding how to assign plain texts, right? The arithmetic, we're going to do arithmetic with the ciphertexts. So when we decode that, all of the arithmetic that has been performed on there is going to happen with respect to the plain text coefficient modules, which is 8 here. What that means is that my coefficients, the numbers over here, can't get above 8. 0 through 7 are the valid values. The way that BFE provides security is it basically maps this plain text space into a much bigger one over here. So it maps this single polynomial on the left over to a pair of polynomials where the coefficient modules is much, much bigger. And that's sort of how we provide security, how we hide the contents of the message and make it difficult to get the plain text message out if you get to look at this thing over here on the right. So when we encrypt this plain text over here, what we're going to get is this ciphertext that has 2 polynomials in it, and each of the coefficients is going to be somewhere between 0 and 2 to the 16th plus 1. That's our coefficient, or that's our ciphertext coefficient modulus, which is called Q, right? So we can do different homomorphic operations using these ciphertexts. So I've got a list of the ones that I'm going to talk about today below. There are a few more, but they kind of get more complicated. But these are the basic things that you would kind of do to compute an algebraic function, right? You can take 2 ciphertexts. So here, when I say capital E with an A inside of it, that means it's an encryption of message A. So if you take an encryption of message A, a ciphertext that's encrypting A, and an encryption of message B, there is a homomorphic addition operation that you can do that produces a valid encryption of the message A plus B. That's what we mean when we say homomorphic addition. It's also pretty easy to start with a ciphertext and add some constant value to it. So here in the second line, the party would know the value B. They would have a plain text for B. And there's another operation you can do to produce an encryption of A plus B, right? And then this also works with multiplication. So if you have 2 ciphertexts, you can perform homomorphic multiplication, and the result that you get there will be an encryption of those 2 messages multiplied together. And again, you can do that with plain text. So the actual arithmetic that you do as a result of those homomorphic operations sometimes get complicated, but for addition, it's pretty easy. So to kind of help you visualize what's going on, I've actually got a homomorphic addition here, and I can kind of step you through it. So we've got over here on the left, I'm imagining that we've got a kind of high side, right? A secrecy area where somebody is doing this encryption and then shipping the ciphertext off to somebody else to do computation on their behalf. So if we start with our two plain text messages of 2 and 2x squared, right? Those are the two polynomials that I'm going to encrypt. And we encrypt them, and we get these two big pairs of ciphertexts over here, or polynomials that are ciphertexts over here. We do the homomorphic addition operation, which is actually really just doing like a pairwise addition modulo this big number up here. So that's kind of hard to see for most of these, but if you look at like this last number here, we've got 4656 is the last number in this first ciphertext, and then 9429. We're basically going to add each corresponding number to itself. So when you sum these two numbers together, you get this one down here. And I promise that all the other ones are also doing modular addition, but that's less obvious if you just like go and look at it, right? So anyway, you add these two ciphertexts together and you get this one resulting down here. And then if we ship that ciphertext back to our encrypting party and they have the secret key, they can decrypt it. They get this message out when they do the decryption, and there you go. There's your addition of these two values together, right? And so what we've effectively done there is we've allowed this party over here on the right side of the dotted line to do some computation on our behalf. And this works not just with addition, and it works not just with pairs of ciphertext. You can bring in plain text in a ciphertext, and you can do multiplication, and you can do some other things. And so basically the way that you use this in practice is you treat each of these operations as a kind of like CPU instruction. And you figure out how to compose those CPU instructions to do some kind of useful algorithm that you want to do. And that's sort of what I'm going to talk through next is two of those useful algorithms that you can do with homomorphic encryption. But before that, I do have some pointers to people who really like math or really like encryption and want to try this out. There are a number of popular open source libraries that you can dig into if you want. The big three that we track are SEAL and Palisade and HELib. SEAL is maintained by Microsoft Research. It stands for Simple Encrypted Arithmetic Library, I think. And so this is definitely the one that I would recommend you start with. It's definitely, I don't think I would call it simple, but it's definitely simpler than all the other ones. It's definitely the most accessible. It's got a kind of well-constructed, understandable API. It was built by software engineers. And it also happens to have the best performance for all of the sort of basic HE operations. So if you want to dig into this a little bit more, I would start there. It supports BFV, which is the algorithm that I'm showing you today, and also CKKS. Palisade is one that was built by several people working on DARPA contracts. New Jersey Institute of Technology has a lot of people. I think there were some like local government contractors who worked on it as well. And it's also pretty good. It is a lot more flexible than SEAL. You can do a lot more different kinds of things with it, but it requires like a much higher level of expertise to actually get anything working. And it kind of implements its own math libraries, which tends to kind of slow it down a little bit for basic stuff relative to SEAL. And HELib is maintained by IBM Research. And I think probably most of the things I said about Palisade kind of applies to HELib as well. But I think you could probably do a little bit more with Palisade. So if you really want to get down to the weeds of the math, maybe you can check out one of these two, but I would definitely recommend you start with SEAL. And I guess one thing that a lot of people ask about is standards, right? So encryption that people use today has things like FIPS and NIST standards. HE is, it's not a new technology, but it's just now becoming something that people in the industry actually want to use. So there aren't any actual standards about it yet. An ISO standard is currently being written by this little standardization body here. So if you want to know more about that, feel free to check them out. Okay, so what can you actually do with all of this stuff, right? Why do people actually sign up to come to this talk? The first thing I'm going to talk about is encrypted search. So the use case here basically is that you can take a SQL query. In this case, I'm going to talk about direct lookup queries, but you can also do the same kind of thing for analytics, and I'll talk more about that later because I know we're all data scientists here, right? We want to do analytics, but we can take a query and we can basically encrypt the query using homomorphic encryption And we can send that encrypted query over to a data owner who has a data set that we don't trust to see the contents of the query. They can process that encrypted query against the database and generate an encrypted response. And that encrypted response, they ship it back to us. We decrypt it, we get the right answer. And if you're anything like me, that sounds like complete magic to you, right? Like I have a PhD in computer science. When Alice and Ann, the CEO of Unveil, asked me to come work at Unveil and do this thing, and she said, yeah, we can take a query, we can encrypt it, we can send it to a database processes the query and sends back the result, and we get the right result, and they never get to see what we're looking for. Like, that sounds like magic, right? I was a database guy. I was like, how are you going to run a query against a database without the database being able to see what you're looking for? So that's really what we use homomorphic encryption for. And I guess, let me step you through this, right? Because it is possible. It's not magic, but there is a good bit of math involved. So anyway, the sort of use case that we're talking about here, here's the big boundary, right, that I'm talking about when I say cross-boundary data science. So there is a component sitting on the left, which is where the user lives, the person who generates the query, or the application that generates this query. And that query contains some sensitive information in it. In this case, I've got this example that I'm using here. It is a banking type of example where there's, ID document numbers and PII, like, somebody's name and where they were born and that kind of thing, right? So these fields in red here are the things that we are interested in protecting with homomorphic encryption using the encrypted query. And the way that the system is going to work is there's a component here inside the trusted boundary that's going to receive this query and encrypt it using HE, and then it's going to ship it it's going to ship it across that boundary to a server that sort of basically knows how to receive the encrypted query and what to do with it in order to process it against the database. Conceptually, the runner of that application is going to be able to look at the query and infer this kind of thing. So they'll be able to see the structure of the query. They'll be able to see what data is getting returned in terms of like what columns are getting returned, right? But they won't be able to see specifically who's being looked for. And they won't be able to see the contents of the response, right? So the way that this works is the size of the encrypted response is padded out to accommodate the biggest possible thing that the user might have asked for, given the parameters of the search that they can see. But the data side of this equation doesn't get to actually see what went into that encrypted response. They get to see that they're shipping encrypted data back, but they don't know whether that contains any hits or, some of this is filled up with hits and some of it isn't. But when the encrypted response goes back to the left side here, where the keys to the homomorphic encryption live, they can decrypt that and they can get the right answer from the query out. So, by the way, I should say the encrypted query does not literally look like this, right? We don't literally take the search terms and encrypt them. That's kind of what I'm going to take you through how we do in a few minutes. But yeah, that's the use case. I am going to talk you through a sort of open source example of how this can be done. Decided to go with an open source example for a couple reasons. First of all, this is going to get posted online, and this is kind of a competitive space. We don't want to tip our hand as to what exactly we're doing. But at Unveil, we do build this same kind of thing. It runs a lot faster because it's optimized for performance, whereas this thing is optimized for you being able to understand it. And so I thought it would be valuable for if anybody was interested. Basically, I'm going to walk you through what's happening in this example. So the database that we have here is just kind of a CSV file. It contains a map of country names to capitals of that country. And then the example that we have here provides a simple little query interface where all of your possible queries are enumerated here on the left. And you click one of them and it runs a homomorphically encrypted query against this data and returns you the result. So how does that actually work? Well, that's what I'm going to step through here. And it's going to be several slides. I guess this will be a good point to pause. Jason, did we have any questions that would be good to dig into now?
There was one question that said, won't the parameters be in the logs?
The parameters. So the way that, I guess let me get through the algorithm. Hopefully that'll explain.
Okay. And the person who asked that question, if you want to clarify, I'll capture it. Mm-hmm. Go ahead, Ryan.
Yeah. So hopefully when I step through the example, it'll be clear how the person owning the server logs can't tell what's actually being looked for. So first, the way this algorithm works is the first step is taking the query and encrypting it using homomorphic encryption. So how do we need to do that? Well, we need to take the contents of the query and we need to map them into a space that's compatible with the BFE plaintext space, which is polynomials, right? So an example of that is on this slide. Basically, we start with the string Ireland. You know, we're gonna look up the capital of Ireland. We're gonna pad that string out to the maximum query length. And here I'm just gonna assume that it's 12. And then we're basically gonna encode each letter there using its ASCII code. And we're gonna get 73, 114, and et cetera. And then we'll get zeros, obviously, where we have our pad. And each of these little boxes here is a valid polynomial, technically, right? We could encode each of those things as a BFE ciphertext. And so I'm going to call this the encode function, right? So you'll see me use this a couple of times later. But so when you see me use encode and a string, remember that what you get out of that is a set of numbers, right? Just a vector of numbers with one number per letter that you're looking for. Okay. So what do we do with that number, with that vector of numbers? We are basically just going to encrypt them directly using BFE with the secret key. And that's going to give us a vector of 12 BFE ciphertexts. I've labeled them, Q0 through Q11 here. Remember, that's kind of, I'm making variables, but under the hood, if you actually send it to the data owner, they see something like this. They see a big array of polynomial coefficients that they can't decode into the underlying thing that you're looking for. So this encrypted query is now safe to transit from the trusted side of that equation to the untrusted side where the data lives. And now we need to figure out, how do we run that matching algorithm? How do we take that encrypted query and process it against the data to give us the right result? And the way that we need to do that is using an oblivious algorithm. So an oblivious algorithm basically is something that the server can run without needing to know, while it's oblivious to the contents of one of the inputs. And so what that basically means is it needs to run without any kind of branches or anything like that. And obviously all of the operations that it performs have to be compatible with the homomorphic encryption. So the sort of interesting part of this is this oblivious letter match function. And this is the part where we're going to get into a little bit of math here. This thing works using a trick that is a consequence of something called Fermat's little theorem. And what that basically says, if you're working with modular arithmetic in the integers, so here we're working with mod t, which is our plain text modulus, right? And you have a input number between 0 and t. If you raise that to the power of t minus 1, the thing that you get if you mod it by t is going to be 1. So if a is between 0 and t, then you're going to get 1 mod t. If a is equal to 0, then you raise that to any power, it's still going to be 0, right? So the way that we are using that trick right here is this oblivious letter match function takes one homomorphically encrypted letter, which is Q, right? When you see something that's highlighted in Q here, that means it's homomorphically encrypted. And it's going to take a plain text letter L that comes from the database's data. And it's going to compute whether they match or not, right? And so what they're going to do, this is the ASCII encoding of this letter, and this is the ASCII encoding of this letter. You're going to subtract those two values. So you're going to get either a 0 if they're the same letter, or you're going to get something other than 0 if they're not the same letter. And we're going to raise this to the power of t minus 1. And because of this Fermat's little theorem over here, what that means is this result that we get, x, we're going to do homomorphic multiplications and homomorphic subtraction here. This homomorphically encrypted x that we get is going to be 0 if Q and L are the same letter. And it's going to be 1 if they are different letters. And then, since what we want out of oblivious letter match is a 1 if they're the same letter and a 0 otherwise, that's kind of the opposite of what we just got. We'll just do a homomorphic 1 minus x, and that's our match, right? So the encrypted result, the ciphertext result that we get out of here, is going to encrypt a 1 if Q and L are the same letter, and a 0 otherwise. And so that's the sort of interesting oblivious part of the algorithm. The rest of it is just kind of building up that into a full matching capability. So next we've got this oblivious word match function that basically takes a vector of homomorphically encrypted letters, which is going to be an encrypted query, and a vector of plain text letters, which is going to come out of the database. And it's going to return a 1 if those two words match. And we're basically going to get that by just running oblivious letter match on each consecutive pair of letters and homomorphically multiplying all those results together. So remember, we can subtract a ciphertext and a plain text, and we can multiply a ciphertext with itself. And so we can do all of this homomorphically. And then the capital M that we get here as a result of multiplying all these things together is going to encrypt a 1 if this full word, this encrypted word, matches this plain text word here. And we can then build that up one layer more and run an Oblivious search, right? So the inputs to the Oblivious search are going to be a vector of encrypted letters, which is just the query that we're looking for. It's going to be this capital D here is the database of the CSV file, basically. It's going to have each record is going to have a country name and a capital name. And then, of course, we've got our max length, which is 12. And so we are basically going to run down each pair of country and capital name in the database. And we are going to start with, an empty vector of all zeros. We're going to run Oblivious word match with our encrypted query, so the country that we're looking for. And then we're going to encode the country in the current line of the database as BFE plaintext. And we're going to run Oblivious word match against those two things. We'll get an encrypted 1 or 0 if they are, is whether they're a match or not. We're not going to be able to see whether that's a match for each line. But we are going to know, because of how the query is constructed, that only one of those lines is going to match, right? Just because in the data, there's no duplicate countries or anything like that. Okay. And then we're going to take that M, we're going to take that 0 or 1, and we're going to encode the capital of the country. Basically, here's where we put in the payload that we want to return with our encrypted result, right? So in this case, we're running a query for the capital based on the country. And so we basically just encode the capital as BFE plaintext and multiply it with the thing that we want, our encrypted match variable here, right? This is where you would slot in any kind of other analytic, right? It's just a general payload. So if you want to do something more sophisticated, like, look up the average population of countries or do some other kind of homomorphic computation, you can do histograms, sums, averages, that kind of thing. You would kind of fit all of that in right here. Anyway, we are then going to have this vector R here. It's our encrypted result. And we're basically going to kind of accumulate that as we run this same algorithm against each line in the database. And at the end of it, we've only had one possible match. So we're basically going to obliviously throw out all of the records that didn't match the thing that we were looking for. And the encrypted response is just going to encode the one thing that we were looking for. So I've got a little example down here in the lower half that kind of shows you what would happen if you ran it against the CSV file that we have. So what we've done with the encrypted query is we basically encoded Ireland and then homomorphically encrypted that. So I'm kind of abusing the notation a little bit here, just to make it clear where we have a match and where we don't. So the homomorphically encrypted thing is an encoding of the string Ireland. The first line of the database is Abkhazia is the country, and Sukhumi is the name of the capital. Hopefully I pronounced those right. So we're going to call this Oblivious word match on the encryption of Ireland and the encoding of Abkhazia. Those are not going to match, right? So the result of this thing is going to be an encryption of 0. And we're going to multiply that with the encoding of Sukhumi, which is going to not change anything. It's going to be encryption of 0. And we're going to do that same thing for all of the lines. And they're all going to be zeros until we get down to Ireland. And when we evaluate homomorphically this Oblivious word match function with the encrypted encoding of Ireland and the plaintext encoded of Ireland that we pulled off of the current line that we're working on, we will finally get a homomorphic 1 as a result of that, or a homomorphic encryption of 1. But we won't know that, right? But when we multiply that in with the encoding of Dublin, the response will now actually be an encryption of Dublin. And that will remain the case as we process the rest of the lines in the CSV file, and the encrypted response that we will return will be an encoding of Dublin. And so when we decrypt that over on the query side, back on the trusted side of this computation, we'll get Dublin out of it. And that's how an encrypted query works, right? That's how you can run a query against the database and have the database return you the exact result that you were looking for without being able to see what you were looking for or what the response is. So I guess I'll pause here and see if there are still any questions. I think, the next thing I have is a demo of that. So I guess why don't I run the demo while we see if there are any questions.
Yeah, there's no questions yet. If anyone has any questions, please post it.
All right, cool. So if you go to that open source library, the link that I provided was for Mac OS. I think they have similar versions for PC and Linux. But basically, it's just an Xcode project, and you run privacy preserving search. This has worked every other time I've run it, so hopefully it'll work this time. Yep, there you go. Okay. So we'll go down here. We'll click Ireland. If I can find it, there it is. All right, so we click run. As I said at the top, right, this algorithm is built for ease of understanding. It's still, frankly, kind of hard to understand, which is why I figured it would be valuable for me to explain it. But it's definitely not built for speed, so it's going to take 20 seconds or so, whereas the same query on our systems would be sub-second. But it does have some interesting stuff that it's printing out in the logs here, and of course, it does let you dig into the code and see exactly how is all of this working, and what's going on with the encryption under the scenes. So anyway, it's taking longer. There we go. Capital Dublin. It worked. Cool. All right. So if we don't have any questions, let me switch back over to the slides and I'll talk through encrypted machine learning. So use case number 2, encrypted machine learning inference. So I'm talking specifically about inference here. So this would mean you already have a machine learning model that you've trained on some data that you have. And that model is sensitive for one reason or another, similar reasons why a query might be sensitive. Maybe the model was trained on some classified data or some regulated data. And so now the model needs to be treated as sensitive because you can extract data from machine learning models sometimes. Or maybe the model was just expensive for you to make, right? You had to hire a bunch of data scientists, you had to pay them a lot of money. And now you've got this machine learning model and you don't just want to give it to somebody else. But you still want to process the model against data that somebody else has for whatever reason. Homomorphic encryption is something that allows you to do that. You would probably use the CKKS homomorphic encryption system because it supports real numbers, fixed point real numbers instead of just integers. But I'm not going to dig too much into that because it's pretty similar. And I mean, the way to do this is kind of straightforward, right? For something like a neural network, that's the example that I have here. A neural network is just a network of individual neurons. And the way that they work is, you have your feature values that are inputs or your inputs to if it's, down a layer in the neural network. And you have some weights and you basically compute a dot product and you feed the result of that into an activation function. And that gives you the output for that neuron. So the way that you do this with homomorphic encryption is you just kind of use homomorphic operations to evaluate some of these things. And, depending on the use case that you have and sort of who's evaluating what, you can do this a little bit differently, right? So the example that I have here, this first one is the input features are the things that are homomorphically encrypted, just like before. If you see something green, that means it's happening homomorphically. And if you see something without a background, that means it's plain text, right? So here the input features are homomorphically encrypted, but the weights are plain text. So this type of use case would be if, actually different from what I said at the top of the slide, sorry. This type of use case would be for if you have some sensitive data and another party has a machine learning model, you want to send the encrypted data to them and they process that model homomorphically and they send you back the encrypted result. And that means that they don't get to see the data that they're working over, which might potentially be sensitive. And you get the result of the machine learning model inference, but you don't get to see their model, right? So that's sort of what we would do here. We basically just homomorphically evaluate that dot product. We would do, homomorphic multiplication of x0 and y0, and then the same thing all the way down this column and just sum them all up. Where it gets tricky is in the activation function, right? So obviously you can use a whole bunch of different activation functions for neural networks. The difficulty with homomorphic encryption is you can only do linear algebraic transformations. You can only do polynomials, right? So any kind of nonlinear thing, any like logistic function or ReLU or frankly most of the things people use inside of neural networks, you would need to use a polynomial approximation of that function, which can be done, and you can actually make those things pretty accurate, but they're only accurate to like specific ranges, right? So this is something that's possible. It's kind of at the edge of what we can do right now. And there's a lot of people looking into how to make it better. But this is how that would work, right? You would homomorphically evaluate either the activation function itself or some approximation of it. And the example that I'm going to take you through uses just x squared as the activation function, so they can get away with that. Another type of use case you might see for this is the thing that I said at first, actually, where somebody has a model that is sensitive and they want to ship that off and process over somebody else's data. That, you know, when that processing happened, that data would be coming in plain text. And then the model owner would get the encrypted inferences and decode them and get the result of the ML inference there. And again, this is pretty much the same thing, except now the features are plain text because this is being run locally to where the data originates, and the weights are homomorphically encrypted because that's what's being protected here. But the rest of this is all the same. And then lastly, we have the thing that the open source example actually does, where the data is encrypted and the weights are also encrypted. And this is something that you might potentially do, frankly, in the future, but you might potentially do it if you wanted to offload processing of the machine learning algorithm to a cheaper system, for example, like something in the cloud, right? But something that you didn't trust to see the underlying data or the underlying model. Homomorphic encryption could potentially allow you to do that. And so again, you know, the IBM FHE toolkit that I linked earlier also has an example of this, so I figured I would just show that real quick. And one of the things that this demonstrates that the other example doesn't is what we call batching, right? So something that I haven't really talked in detail about, but is really important for homomorphic processing is because all of these plain text and ciphertext are big polynomials, people have figured out optimizations that basically allow you to pack a bunch of independent plain text values in there that are basically the size of a single coefficient and kind of work on them independently. So what's happening behind the scenes here is we have a machine learning model that is programmed to recognize credit card fraud. It's called the credit card fraud demo, right? So you've got transaction data and you've got basically a neural network that's looking at features and trying to say, is this fraud or not? And we're evaluating all these predictions homomorphically, and we're evaluating big batches of them in one go. So you see the first batch here has completed while I've been talking, and it's evaluated 512 examples. And we found, you know, one positive prediction, and no, we just had another batch finish. But you know, a whole bunch of negative predictions, right? Obviously, fraud is thankfully not that common. But anyway, this is a good example of how you can leverage batching to get a single set of homomorphic operations that do kind of like single instruction, multiple data kinds of optimizations. So yeah, this is going to take a long time to fully finish, so I wasn't going to sit here and let it run. But that is encrypted ML processing. As I've sort of alluded to, there's a good number of limitations in this still. So as I said earlier, you can only compute polynomial functions directly with CKKS. So what that means is you need to basically do a polynomial approximation if you're doing anything nonlinear for your activation function. This is only really practical for low depth models. This kind of relates to some of the current limitations around homomorphic encryption systems in general. And there are also, interestingly, extra security constraints due to some of the properties of CKKS. So one of the neat things, well, one of the interesting things is that when you get a result of this encrypted computation, you kind of need to treat that as secret. And the reason is that the way homomorphic encryption works, it protects your data by encoding it with noise. And the contents of the noise that you get out of those homomorphic operations can sometimes give away some of the operations that were done in the other space, right? So you can use the noise to kind of make some inferences around what's actually done. And sometimes you can even use it to get the secret key out. So basically, there's some extra security things you have to worry about sometimes when you're working with homomorphic encryption. But you know, all of these problems are eminently solvable. It's just going to take some time to solve them. And I really do think that you know, in 5 or 10 years, we'll start seeing some really cool machine learning applications of HE. So that's everything that I had planned to run through. Happy to take any questions now, but you know, while I have you here, the main thing I want to say is Enveil is hiring. So if you found any of this stuff interesting, please consider shooting me an email at ryan@nvel.com or careers@nvel.com. We're hiring software engineers, customer success people, PMs, sales. We build tools that data scientists use, right? So if you want to be a software engineer, if you have data science experience, that is valuable. But the sort of work that we do is definitely software engineering work. And yeah. So anyway, thanks everybody for your time. Jason?
So there was a couple of questions. The first question was, is it fair to say that you have to implement the same encoding logic on both the trusted and the untrusted sides?
Yeah, for encoding data into plain text. Mm-hmm.
Okay. And then this was actually a question, but I also had the same question. Is there a how's the performance when you introduce this? Like, is there a lot of latency introduced? Does it impact like real-time systems? Do you see this being used in real-time systems?
Good question. So the performance, there's definitely a sort of big performance overhead for homomorphic operations relative to plain text operations. So this is not something where you would take an existing workflow and replace it with a homomorphic encryption workflow, right? This is something where homomorphic encryption would allow you to do a completely new use case that you wouldn't do before. So in terms of like, what is the overhead versus an existing system? That's something where I kind of feel like, well, that's not the right question to ask, right? So the systems that we build absolutely can return queries, sub-second for a lot of data sets. But it gets interesting because that problem scales differently, right? The problem of processing an encrypted query has a fundamentally different structure, because you're doing that oblivious processing, has a fundamentally different structure than a plain text query where you can see what you're looking for and you can leverage something like an index, right? So real-time systems, we don't really target those with sales at the moment. I think we will get there. But no, we're looking primarily at systems where the analysts can afford to wait like 3 seconds to 10 seconds. We can usually get done if we have that much time.
Okay. There was a question, is this military grade encryption?
That's a good question. I don't know exactly what military grade means. We come out of the NSA. NSA has something like Suite B, you might have heard of, right? So those are standards, right? There aren't standards around HE just yet. There's an ISO standard that's like being worked right now. And, for us, we do a lot of work with the US military and Unveil. So we do have sort of onesie twosie authority to operate on government systems in certain places. We've kind of pushed through that, but there's no like published standards around HE yet. That's sort of the big hump that we're trying to get over as an industry. And I think we will get there shortly because, the NSA knows that this can all be done securely, right? It's just a matter of going through the motions and getting it through the sort of bureaucracy. One other thing I'll say around security of HE that I haven't said yet, a lot of people are worried about quantum computing, right? There's going to be a big sort of shakeup at one point in the hypothetical future when quantum computers become practical. And the reason for that is there are algorithms that require a quantum computer that can break a lot of the encryption that is used today. So AES and RSA and things like that. The math problems that HE is based upon are lattice problems. And those are thought to be quantum resistant. So that basically we think that having a quantum computer isn't going to help you in terms of breaking the security there. So lattice-based things are sort of the prime candidates for post-quantum crypto, which is another reason why the government is motivated to kind of move forward with standards around this. So sort of, I do think it's actually more secure than a lot of the crypto that we're using today. It just hasn't made it through the bureaucracy quite yet.
You said there was a lot of research taking place. Can you name any of like some of the areas? Are people trying to attack this, or are they trying to expand this, or trying to come up, like what are the things that people are working on?
Yeah, good question. So there's certainly a lot of people who are trying to attack it. Crypto researchers in general are trying to break things. There are a lot of people who are trying to solve some of the practical constraints around using it, right? And it gets very complicated very fast, so I haven't gotten into it much as part of this talk. But basically, there's a limit on the number of homomorphic operations you can do with a given ciphertext that has to do with the way that you provide security in homomorphic encryption. You encrypt it with a little bit of noise. And so basically, as you do homomorphic operations on a ciphertext, the noise that's kind of built into that ciphertext grows and grows and grows, and eventually it can kind of swamp out all of the data encoded in that ciphertext, particularly if you do like a lot of multiplications with it. So there's a lot of active research around solving that problem, making that noise growth happen more slowly or not happen at all. There's a lot of people working on specific applications of it, like us. There's a lot of people working on deep learning with homomorphic encryption. There's a lot of people working on hardware acceleration of homomorphic encryption to try and solve some of the sort of overhead relative to plain text processing. So yeah, tons and tons of stuff is going on. It's a really fascinating field to be in.
So you might have answered this. There's always an interest of like how to get started. Would you use the 3 open source that you recommended, and is that how someone would kind of get familiar with this area and start playing around?
Yeah, I would definitely check out Microsoft Seal. They've got a good README. I would definitely check out that FHE example page that I linked to. I can probably just back up and see the slide. Here you go. So yeah, that has an actual like thing that you can compile and run and then kind of try and dig into yourself. That's doing an actual, the Seal is a library, but this is an actual working application that's actually doing something that you can dig into. So yeah, I would definitely check out those 2 things.
Are there a lot of resources? Like it feels like a complicated area and maybe not necessarily the most well documented. Do you find that there are good books or resources or, I don't know, forums or something that people are using to talk about this and learn?
Books, no. That's something that, frankly, the complexity in explaining it to people is one of the biggest challenges we've faced as Unveil. So yeah, unfortunately, it does require a little bit of dedication and a little bit of like, being really interested in what it can do to get into, because you can get there. But it is going to involve kind of digging into a lot of GitHub repositories, a lot of issues. There are not good books around it yet, for example.
That makes sense. And then there was one. If anyone else has any questions, please ask. But there is one more question about: are you seeing people build like hybrid systems where they're using the HE for just the sensitive portion, but kind of mixing that with a more traditional, I guess, like query system?
Yeah, certainly. Like for an example, if you're running encrypted queries, right? If you have a sort of pipeline between those 2 parties set up, and there is a query that's not sensitive, you can certainly run that without HE right now. Yeah. And then when you are doing your homomorphic processing, obviously any data that kind of lives on your system, there's no reason to kind of encrypt that, right? You can just do plain text processing on that. So yeah, that's actually something where we kind of disagree with some other people. Some of our competitors in the industry, what they wanted to do, their first step in their homomorphic encryption system was just take all your plain text data and homomorphically encrypt it and put it in the cloud, and you can work on it there. But anyway, yeah, no, I agree. It definitely makes sense. Don't homomorphically encrypt anything unless you absolutely have to.
Or have you? I don't know if you can talk about this. I was just curious. Are you seeing a lot of growth in the usage of HE and stuff? Like, are you seeing more and more customers and more areas actually find that this is necessary?
Yeah, we're hiring.
Yeah, well, yeah, that's a good point. Yeah.
Yeah, no, we have kind of like doubled year over year. So yeah, there's definitely growing interest in this area. Both, for Unveil as a business, but also like our competitors are also doing fine too. And so, yeah, I think there's a lot of push. Where's my slide that I have this, right? So, we've got Gartner. We talk with Gartner a lot more than a lot of other places, than like most other industries, right? So analysts are very heavily focused on this. They do see a lot of demand coming down the pike. And then definitely internally in the federal government, there are just a million use cases for this, right? There are a million little silos of data. There are a million barriers to people interacting with data sets, and this can solve a good chunk of them. So yeah, it's kind of greenfield for us. We've been doing.
Yeah, I hate to say this. It kind of reminds me, or makes me feel at least like blockchain, where it was at the very beginning, where it was only a small set of people understood it, but then it became everything was blockchain. I'm just wondering if you're going to see rapid growth in this and more people get interested in this and becoming focus area for folks, like people really becoming experts in this area.
That wouldn't surprise me. Yeah. Yeah.
Okay. I don't see any other questions, Ryan. I'm just doing a double check. Well, this was really awesome. I mean, this is really interesting, and it is very complicated, and I probably have to look at this a couple of times. But if anyone has any questions, or if you're interested in learning more about Unveil, please reach out to Ryan. It sounds like they're hiring, and look, no time tracking, and you'd be working on some very interesting problems. If you need anything from me, Ryan, just let me know. But thank you so much. It was a great talk, and thank you for everyone that joined us. And I hope to see you guys in next month. Thanks, Ryan.
Thanks, everybody. Thanks, Jason.